Welcome everyone. In a previous lesson, we understood how to compute the continuous time Fourier series. In this lesson, we will understand how to use the properties of the continuous time Fourier series to actually compute the Fourier series of new signals based on our knowledge on the Fourier series coefficients of some existing signals. Then we will look at briefly Parseval's theorem and then briefly on convergence of Fourier series. Okay, think about a signal, periodic signal xt with period t, and its fundamental frequencies omega naught is 2 pi divided by t. Then its Fourier series coefficients are denoted by ak. Then we can write in shortened form as ak has its Fourier series coefficients ak with this calligraphic fs to say Fourier series. Okay, so we have xt, its Fourier series coefficients ak, and yt, which also has the same period t, and its Fourier series coefficients are bk's. So any linear combination of the two signals will also be periodic with period t, and the Fourier series coefficients of this linear combination ck would be related to the Fourier series coefficients ak and bk. And how are they related? In this fashion. So if zt, our new signal, is a times xt plus b times yt, where a and b are constants, then ck would be a times ak plus b times bk, a very obvious relationship. Okay, then as the next property, we will look at the time shifting property. So what we want to do here is, using our knowledge of the Fourier series coefficients of xt, we want to find the Fourier series coefficients of x t minus t naught, this time shifted version of xt. Okay, so we remind ourselves that xt can be expressed as its Fourier series ak times e to the power of jk omega naught t, and we can compute these ak's by 1 over t integral over a period xt e to the power of minus jk omega naught t dt. Okay, so let's do a brief proof on this. So xt's Fourier series coefficients are ak's, and let's consider that xt minus t naught's Fourier series coefficients are bk's. So let's try to find these Fourier series coefficients using this formula. In order to do that, instead of xt, we must write xt minus t naught, because that is the signal that we want to find the Fourier series coefficients of. And then we have to multiply that with e to the power of minus jk omega naught t and integrate it. Okay, and then we will do a substitution. We'll write tau equals t minus t naught. So therefore you know that d tau is equal to dt. So we replace t minus t naught with tau, and our t would become tau plus t naught. Then we realize that e to the power of minus jk omega naught t naught, because of this term, is independent of the integrating variable tau. Therefore we can take it outside the integral sign, and therefore we have this form. And then we realize this actually is ak, because tau is just a dummy variable. So therefore bk is equal to e to the power of minus jk omega naught t naught ak, which is our property that we wanted to prove. So you will notice that since the magnitude of e to the power of jk omega naught t naught is 1, ak's magnitude is the same as bk's. So therefore here you can see there is a phase shift only. Okay, then we look at the time reversal property. So we know that xt's Fourier series coefficients are ak, we are given that, and now we want to find the Fourier series coefficients of x minus t. Actually they turn out to be x a minus k. So how do you do that? So x minus t can be written as its Fourier series by writing ak e to the power of minus j k omega naught t. So we did that by writing, instead of t, here minus t. Okay, then substituting k equals minus m, we get this formula. So here m goes from minus infinity to infinity, still a minus m e to the power of jm 2 pi over capital T. So we know that 2 pi over t is actually omega naught. So this we see has a form of the Fourier series synthesis equation for x minus t. So therefore bk is equal to, bk's are equal to a minus k's, because of this a minus a. Okay. Time reversal applied to a continuous time signal results in the time reversal, actually reversal in k, of the corresponding sequence of Fourier series coefficients. If xt is even, that is x minus t is equal to xt. For example, if we take the cosine signal, that's an even signal. That means when you reflect it over here, you get the same thing. Then its Fourier series coefficients are also even. That is a minus k is equal to ak. So if xt's Fourier series coefficients are ak, we know that x minus t's Fourier series coefficients are a minus k, because of the property that we established in the previous slide, and these are equal. Okay, if xt is odd, for example, the sine signal is an odd signal. If you reflect here, you get the negative of the signal. X minus t is equal to minus xt. Then its Fourier series coefficients are also odd, because if ak's are the Fourier series coefficients of xt, then x minus t's Fourier series coefficients are a minus k's, as we saw before, and these are equal, and here there's a minus sign. Okay. Then time scaling. Time scaling in general changes the period. If xt is periodic with period t and fundamental frequency omega naught t is equal to 2 pi over t, then x alpha t, where alpha is a positive real number, is periodic with t divided by alpha, and the fundamental frequency is alpha omega naught. So if you take the Fourier series representation of x alpha t, k goes from minus infinity to infinity, ak e to the power of jk alpha omega naught t. So while the Fourier series coefficients have not changed, the Fourier series representation actually has changed, because the frequencies have changed. Okay, then the multiplication property. So I will not explain this in detail or use this right now. So we would be able to understand this when we think about convolution of discrete time signals. But just for the sake of completeness, we will just go through this. So let xt and yt denote two periodic signals with period t. So xt has a Fourier series coefficients ak, yt has a Fourier series coefficients bk. Since the product xt times yt is also periodic with t, its Fourier series coefficients hk are, see, L goes from minus infinity to infinity, al bk minus L. To find one Fourier series coefficients hk, you must run an infinite summation from L goes from minus infinity to infinity. Okay. All right. Now let's look at conjugation and conjugate symmetry. So if you have a complex number 4 plus 5j, its complex conjugate is 4 minus 5j. So no. So taking the complex conjugate of a periodic signal xt has the effect of complex conjugation and time reversal on the corresponding Fourier series coefficients. So what this means is, if xt is real, then we know that xt is equal to x star t, the complex conjugate. So if you take a real number like 4, for example, just complex conjugate, getting the complex conjugate does not matter, you get the same thing. Fourier series coefficients are conjugate symmetric. That means a minus k is equal to ak star. Okay. So now if xt has the Fourier series coefficients ak, then what this property said was that x star t has the Fourier series coefficients a minus k star, because complex conjugation and time reversal, actually k reversal happens. Yeah. So there you go, we have xt equals to a star t. What that means is xt's Fourier series coefficients ak must be equal to a minus k star. So therefore you can deduce this relationship. Okay, that is if xt is real. If xt is real, then a naught is real and ak's magnitude is equal to a minus k's magnitude, because of this reason. If xt is real and even, now we know that xt is real. If xt is real, we have this property, and also if it is even, that means if it is even, we know that xt is equal to x minus t. Yes. So we know that ak is equal to a minus k from the property that we saw previously on time reversal. See, then when we combine these things, two things, from evenness we get this property, from realness we get this property, and then if we combine, what do we get? We get ak equals ak star. That is, if xt is real and even, so are its Fourier series coefficients. So if xt is real and even, Fourier series coefficients are also real and even. So this shows that they are even. This shows that they are real. So if xt is real and odd, its Fourier series coefficients are purely imaginary and odd. Thus, a naught is also 0. Okay, so we can take the simple examples once again. First of all, we can take x1t is equal to cos omega naught t, which is a real and even signal. So this is the plot of that signal. So you can see it is actually an even signal. So it does not have an imaginary part. So therefore, this signal is a real signal. So if we take the Fourier series coefficients of this signal, actually how do we do that? So we write x1 t as using the Euler's relationship, e to the power of j omega naught t plus e to the power of minus j omega naught t divided by 2. So therefore you know that a1 is equal to half, a minus 1 is equal to half, all other a's are 0 when for a for k not equal to plus or minus 1. So therefore you have half here and half there. So you can see this is a real and even signal. and the Fourier series coefficients are also real and even. That means if you reflect over here, you can see it is even and they are real numbers. Now let's consider the sine omega naught t. For this, you know that x2t is equal to e to the power of j omega naught t minus e to the power of minus j omega naught t divided by 2j. So therefore a1 is equal to 1 over 2j, a minus 1 is equal to minus 1 over 2j. So therefore we have plotted them right here. Actually we need the magnitude and the phase to plot them, but for convenience we are plotting it like that, indicating the j part also as the magnitude. So this signal is an odd signal. You can see when you reflect you get the negative of the signal, and it is real because there is no imaginary part in the signal sine omega naught t. So when you think about this, so Fourier series coefficients are all imaginary, and you can see they are odd. So when you reflect it, you get the negative value. So for a real and even signal, Fourier series coefficients are real and even. For a real and odd signal, Fourier series coefficients are purely imaginary and odd. Okay, now let's look at the Parseval's relationship for a continuous time periodic signals, Parseval's relation. So that states that if you take the average power x magnitude squared dt integrating over one period is equal to actually the square sum of the magnitudes of the Fourier series coefficients. So left hand side of equation 8 is average power, that is energy per unit time in one period of the periodic signal xt. So we can take one harmonic and we can do a brief justification of this. So let's think about this. Now let's write xt as its Fourier series. So k goes from minus infinity to infinity, ak e to the power of j k omega naught t. So out of these infinite number of harmonics, let's take one of them and write it here, and we write it as square because of this, an absolute value also. And then you will notice that the absolute magnitude of e to the power of j k omega naught t is 1, so therefore you get ak squared, and then when you integrate this constant divide by over the period t and divide by t, you get ak squared. So for the kth harmonic you get ak squared, for the other harmonics also you get the similar expression. So therefore you can see this is the summation that you get on the right hand side for the different harmonics like this. So this is not a full justification. So you have to understand when you multiply signals of harmonically related signals and integrate what happens to them, but we will not consider that development here. Thus what Parseval's relation states is that the total average power in a periodic signal equals the sum of the average powers in all its harmonic components. Okay, so later on we'll do an example for this. Now let's take an example to use the Fourier series properties to find the Fourier series of an unknown signal by using the knowledge that we have of the square wave and its Fourier series coefficients. Consider the signal gt with the fundamental period 4 as shown in this figure. So you can see fundamental period from here to here, it's 4. Determine the Fourier series representation of gt directly from the analysis equation by assuming that the Fourier series coefficients of the symmetric periodic square wave are known. Okay, so the direct solution, I will directly write it. So you note the average of that signal is 0. So a k is 1 over 2 pi jk, 1 minus cos k pi. So if you write for different values, when you put k equals 1, you get minus j over pi, a2 is 0, a3 is minus j over 3 pi, a4 is 0, a5 is minus j over 5 pi, and so on. Okay. Now to get this from the knowledge of the Fourier series coefficient of the square wave, we can find the relationship between the square wave and this signal. For the square wave that we studied earlier, if we think that the pulse goes from minus t1 to t1 and the period is t, magnitude is 1, and if this is xt, we know that its Fourier series coefficients a naught is equal to half. For this condition, ak is equal to sine pi k divided by 2 divided by k pi when k is not equal to 0. So what you want to do is to use this knowledge to find the Fourier series coefficients of this waveform, which is gt, which is actually like this. Here the value is minus 2, time value is 2 here, this is time, and this is half, is minus half. So you can see here, if I consider this to be 1 and t to be 4, if I time delay this by 1 and subtract half, you get a gt. So there you go. Now we have the relationship. Now we can use this and the knowledge about Fourier series properties to find the Fourier series coefficients of gt. Okay. So let's consider xt, that xt has a Fourier series coefficients ak. Then dk's of xt minus 1 would be using the time shifting property. That means if xt has the Fourier series coefficients ak, we know that t minus t naught has a Fourier series coefficients e to the power of minus j k omega naught t naught ak. So using that relationship, we can find that here, of course, t naught is 1. So therefore, and omega naught is equal to 2 pi over 4, that is pi over 2. We get this. So the Fourier series coefficients of the offset minus half would be, it's a DC value, c 0 for k not equal to 0 and minus half for k equals to 0. Then applying the linearity property, the Fourier series coefficient of gt may be expressed as, because it is a linear combination of this and this. So ak to the power of minus jk pi over 2 for k is not equal to 0, because here they are 0 and here you have minus half, a naught minus half. So if you take a naught here, you get it's actually 2t1 divided by t for x t, so it is actually half, so this cancels off and you get 0. Okay, so that is the solution. So if you want to be convinced, you can put values for k's and find out that they are actually equal to this. which I will not do. Okay. Then as the next example, consider the triangular wave, a signal xt with period t equals 4 and fundamental frequency omega not equals to pi by 2 as shown in this figure. The derivative signal is the signal gt in figure 5. So if you take the derivative of this, so let's plot the derivative of this signal. So let's just start from here. So it's from 1 to 0, it decreases in a period of 2. So therefore this is minus half, and then this increases from 0 to 1 over a period of 2. So that is, it is half. So you can see this is the signal. Okay, now we are familiar with that. We know its Fourier series coefficients. The derivative of this signal is the signal gt in the previous example, denoting the Fourier series coefficients of gt by dk and those of xt by ek. We see the differentiation property indicates that. So actually we did not take down the differentiation property. So I will show you the table of properties later on. So for the differentiation property, d by dt x t has the Fourier series coefficients j k omega naught ak. So dk is then related to ek because of this relationship jk pi by 2. This equation can be used to express ek in terms of dk except when k is equal to 0. Specifically, ek is equal to 2 dk divided by jk pi. That means 2 sine pi k by 2 divided by jk pi squared. So using this and dividing that by jk pi and multiplying by 2. So for k equals 0, E naught can be determined by finding the area under one period of xt and dividing by the length of the period. And we can just look at this and find E naught. And that turns out to be half. Okay, as a next example, we will look at the Fourier series coefficients of the impulse train. So now let's try to try to understand that this xt is actually plotted here. So as we know, the graph of delta t is this. So we draw an arrow. You know that the integral is 1 of the signal. It's not the magnitude that we are talking about. And then if you want to write delta t minus capital T, and then you will have nothing at 0, but at t you will have an impulse of 1. Then delta t plus t, if you consider at 0, this at minus t, you will have an impulse of 1, and so on and so on. So you can see if you sum all these things, you get this. Okay. So now we see this as a periodic signal, and we can consider the period from minus t by 2 to t by 2 and apply our formulas to obtain the Fourier series coefficients. To determine the Fourier series coefficients ak, we select the interval integration to be minus t by 2 to t by 2. Within this interval, xt is the same as delta t. So within this interval, we only get this part, so it is the same as delta t. So then ak is equal to 1 over t, integral from minus t by 2 to t, delta t to the power of minus j k2 pi over t. So you know that when you have to integrate delta t with multiplied by another signal, you get the signal So delta t minus t naught and multiply by that by xt. In practically, you can just consider xt naught. So you put here, so t is missing here, so t is equal to 0, so you get 1 over t is equal to 1. So what we are applying is this, so ak equals 1 over t integral of t xt e to the power of minus j k omega naught t dt, Fourier series coefficient finding formula. Okay, in other words, the Fourier series coefficients of the impulse train are identical. These coefficients are also real valued and even with respect to the index k. So they are its constants 1 over t. Okay, so now let's take one more example. By expressing the derivative of the square wave signal in terms of the impulses, obtain the Fourier series coefficients of the square wave signal, which we have done analytically. Now let's use the Fourier series properties to do that. So if you think about the derivative of this, so right here there's a transition from 0 to 1, so we can consider that it's an impulse like this here, transition from 1 to 0, this one, like this. Okay, so now we can consider this as a sum of two impulse trains. They are time shifted. Then we can obtain the Fourier series coefficients using that knowledge. Okay, so here is the derivative of that signal, and then we may interpret qt as a difference of two shifted versions of the impulse train xt. That means qt is like xt plus t1 minus xt minus t1. So therefore, Fourier series coefficients bk of qt may be expressed in terms of the Fourier series coefficients ak of xt, that is e to the power of jk omega naught t1 ak, and this minus sign e to the power of minus jk omega naught t1 ak. So omega naught is 2 pi over t. So therefore you have this, and then we know that for the xt which is the impulse train, Fourier series coefficients are turned out to be 1 over t, right here. So when you combine this, we see that it is from Euler's relation, we can write it as a sine k omega naught t. Okay. Since qt is the derivative of gt, we can use the differentiation property. Bk equals jk omega naught ck, where ck are the Fourier series coefficients of gt. Thus, ck is equal to bk divided by jk omega naught equals to j sine k omega naught t1 divided by jk omega naught and t. So this is what we wrote over here. Okay, so we got the formula. So I hope you remember that these are the Fourier series coefficients of the square wave. Since C naught is just the average value of gt over one period, so we can write it like that as well. Okay. So now let's take an example of the Parseval's relation. For the waveform xt, obtain the full expression for the exponential Fourier series coefficients ak, compute the average power, verify Parseval's relation. Given sum of the reciprocal of positive square integers is, that means if you sum 1 over k squared from k equals 1 to infinity, you get pi squared by 6. This result must be used to verify the Parseval's relation. So here is the signal. So you can see this is the period. So it goes from minus a to a. So we'll use the analytical formula to find out the Fourier series coefficients first. So computing ak first. So a naught is 1 over t integral over txt dt. So we actually, it turns out that this signal can be written as this. So let's just verify this. When t is equal to 0, you have minus a. When t is equal to capital T, you get plus a, right? So this is correct. So therefore we put that over here, and then we have to integrate. So 2t squared divided by 2t minus t, and you get 0. Even when you just look at it, you will see the average value is 0. Okay. Now we need to find AKs. So AK is equal to 1 over t xt to the power of minus jk omega naught t dt. So we substitute for xt this value 2t divided by t minus 1 e to the power of jk omega naught t minus. So we have to use integration by parts. Take this as u, take this as dv. So uv, this is uv, and we have to include the limits, and v du. So derivative of this is 2 over t, this part. The integral of this is that. So now we need to apply the limits. So remember omega naught t is equal to 2 pi. For this we need to put 2 pi. And then when you simplify this and put these two also together and apply 2 pi, you get aj over pi k. So we have formula for a naught, which is 0, and ak aj over pi k. So first part is complete. So here is the answer. So now we need to compute the average power. To compute the average power, you need to get the magnitude of xt, square it, and integrate it, and divide by 1 over t, divide by t. So a squared by t, 2t over t minus 1 squared dt. So I got this square here. I hope it is correct. Yes, and then you integrate. Integration is done over here, and limits are already applied here. So you get a squared over 3. So now we want to use the Fourier series coefficients, and we do the summation with the magnitude, square it, and sum, and see verify whether Parseval's relation is correct. So sum of ak squared, ak magnitude squared. So ak magnitude is aj divided by pi k squared. So because of the magnitude, j disappears, and 2a squared pi squared 1 over k squared. For this we have been given the formula, and then you get a squared over 3, which verifies the Parseval's relation. Okay, then there are these other forms of the Fourier series. It is very important to know these things also, and the relationship between the complex exponential Fourier series that we studied. So complex exponential Fourier series has the form xt equals k goes from minus infinity to infinity ak e to the power of jk omega naught t. So, and we compute ak by 1 over t integral over 1 period xt to the power of minus jk omega naught t dt. Then you have the trigonometric Fourier series. So that you can obtain by using the Euler's relationship here. Xt equals a naught to summation k goes from 1 to infinity ak cos k omega naught t plus bk sin k omega naught t. So therefore actually a naught is equal to this a naught here, what we get, and capital AK is equal to AK plus a minus k divided by 2. So you can see why you get that, because of the, when you apply the Euler's relation, you can get this bk equals jak minus a minus k divided by 2. So then you have the harmonic Fourier series for real x xt. C naught plus 2 k goes from minus 1, k goes from 1 to infinity ck cos k omega naught t minus theta k. So c naught is a naught, ck is ak squared plus bk squared, these values, and theta k is equal to tan inverse bk divided by ak. Okay, then let's briefly look at the convergence of the Fourier series. So these are the Fourier series synthesis and analysis equations. They are very familiar to us now. Now we consider the Fourier series representation and finite series rather than taking k values from minus infinity to infinity, we take from minus n to n. Then let En denote the approximate error that is from the actual infinite representation, subtract the finite representation, so there must be some error here. That error will denote like this. If xt has a Fourier series representation, then the limit of En as n goes to infinity is 0. If xt does not have Fourier series representation, then the integral that computes ak may diverge. Moreover, if all the coefficients ak obtained are finite, when these coefficients are substituted into the synthesis equation, the resulting infinite series may not converge to the original series xt. So this one of these two. Fortunately, there are no convergence difficulties for a large class of periodic signals, continuous and discontinuous, that we usually encounter. So first, finite energy conversion criterion. One class of periodic signals that are representable through the Fourier series is those signals which have finite energy over a single period. So if you integrate it, take the magnitude and square it and integrate it, it's finite. In this case, Fourier series coefficients AKs are finite. As n goes to infinity, En goes to 0. This does not imply that the signal xt and its Fourier series representations are equal at every value of t. What it does say is that there is no energy in their difference. So if you try to construct the square waveform using the formulae that we derived, you will see that you will have things like that, right? Ripples. So you can see at these points, the Fourier series representation and the actual signal are not equal. But as you keep on adding more and more sinusoids, this become extremely thin. However, since physical systems respond to signal energy rather than the value of the signal, from this perspective, xt and its Fourier series representations are indistinguishable. Sorry. So then you have the Dirichlet conditions. Dirichlet conditions guarantee that xt equals its Fourier series representation except at isolated values of t, for which xt is discontinuous. At these values, the infinite series converges to the average of the values on either side of the discontinuity. Over any period xt must be absolutely integrable. That's condition number 1. So take the absolute value, when you integrate it must be finite. This guarantees that AKs are finite. Condition 2, in any finite interval of time xt is of bounded variation, that is, there are no more than a finite number of maxima and minima during any single period of the signal. Condition 3, in any finite interval of time, there are only a finite number of discontinuities. Furthermore, each of these discontinuities is finite. So Oppenheim book has examples of this plotted. So we can see these examples briefly. So first signal, you can see that violates condition 1. The periodic signal with period 1 with one period defined as this. So if you look at this signal, you can see when t is 0, this is infinite, and when t is 1, it is like this. So like this, right? This is that signal. The periodic signal with period 1 with one period defined as sine 2 pi over t. So you see, so you have 1 over t here. Because of this reason, at 1 you have a nice sinusoid, but then you can see oscillations become faster and faster here. So like that. So that's an example of the condition number 2. And for the condition number 3, signal of period 8 composed of an infinite number of sections, each of which is half the height of and half the width of the previous section. Thus, the area under one period of the function is clearly less than 8. However, there are an infinite number of discontinuities in each period, thereby violating condition number 3. So this signal is slightly hard to draw. So if you take the period as 8, so like this, and then to here signal is like this, then up to here signal is like this, then up to you can see what this means. Okay. So in this area, so many discontinuities up to 8. Okay. So today what we considered were the properties of the Fourier series, and there are many properties like time shifting property, time scaling property, linearity, time reversal property, uh, integral property, derivative property, and all these properties. And these properties are in the tables which I have uploaded in the GitHub also. So you can see these tables. Over here. So I have listed all these tables. See the time shifting property, and then conjugation, and then time reversal, and differentiation property, the integration property, and the conjugate symmetry, and so on. All these things are listed here. So in an exam situation, I will give you these sheets, so therefore you don't have to memorize this. Okay. So by using the properties, we can find the Fourier series coefficients of signals based on the knowledge of the Fourier series coefficients of some simple signals like the square waveform, the impulse train, and so on. And we did examples for those. And afterwards, we looked at the Parseval's relation, where we can consider the average power of a signal and the relationship to the Fourier series coefficients. And then we looked at some convergence criteria. Okay, thank you.